Hello everyone. Today we're going to discuss Chapter 18 of our EasyBuilder Pro user manual. This video will serve as the third part of our macro series in which we'll discuss how to use macro function blocks both within and outside of our macro workspace. This will be followed by an introduction to macro debugging and then a demonstration of data conversion. We'll begin by opening EasyBuilder Pro and then our macro manager. To access existing function blocks or create new ones, we'll need to open our macro function library by selecting our Library button. Once this is open, we'll have access to our function library. And before we dive in, let's discuss what a function block is. As stated within our user manual, a function block is a user-defined function that's used to reduce repetitive code. The best way to think about a function block, also referred to as subroutines, is to regard them as a user-defined version of one of our API functions. And although it's true that function blocks reduce repetitive code, they also have several additional uses that we'll discuss in a few minutes. Within our function library, there are two ways we can add a new function block: within our project or within our global library. Our global library is a way to store function blocks so that they can be accessed from other projects. For our introduction, I'll select our global library and then select New to create a new function block. In our last two videos, we focused on our macro workspace. Today we'll be using our function editor, which is different both in structure and application. The general format for our function block begins with a substatement. This is followed by the data format of our return value, and after this we'll specify the function's name, and this is used to call the function within the macro script. Once this is defined, we can create parameters for our function. Parameters are used to give your function structure within your macro workspace, and we'll demonstrate that within a few minutes. Once our parameters have been defined, we can then create local variables that can be used within our function block. And below this is where we'll define our statement. And like our macro workspace, we can call some of our built-in functions to help us build our statement. Our function block is closed by the statement end_sub. And since we already have a variety of skills from part 1 and 2 of our macro series, we'll move forward and create our first macro function block. Let's start by giving our function a name. For this example, we'll go ahead and name our function add. And I'll leave the variable type as short, and we'll go ahead and define some parameters. Our first parameter will be a short, which I'll name x, and next to this I'll place a comma, and then define a second parameter and call it y. Now I'll define a local variable, which will be a short integer. I'll call it result. Now we'll go ahead and define our statement. I'll type result equals x plus y, and then I'll hit enter and type return result. Our function block, as it is now, will add two integers defined within its parameters and return the result. Now that we've created our add function block, we'll go ahead and open our macro workspace so that we can test our function. With our macro workspace open, I'm going to create a short result variable and then call our function on the next line. This is where we'll see the importance of our function's parameters, as they provide a structure in which we can enter our variables or insert numeric data directly. I'll assign our result variable to our function, and insert 2 integers within our function's parameters. If you followed me up to this point, then you now know how to create and use a user-defined function within our macro workspace. Let's go ahead and create a set data for our result variable and set our result into LW0 register. With that finished, I'll save and compile my macro and then create an LW0 numeric object. After quickly checking the data type, I'll go ahead and run an offline simulation. As you've probably noticed, I haven't defined how my macro will execute. Thankfully, since I'm working with our CMT series, I can execute our macro using our CMT diagnoser. To do this, I'm going to right-click on our simulation and select Diagnoser. Once our diagnoser is open, I'm going to select our macro tab, and as I've discussed in a separate video, our CMT series supports real-time macro debugging, which includes execution, monitoring variables, and online changes to our macro. We'll begin by running a simple execution, which will add both integers and return the result of our function into our LW0 register. And as expected, our result is the addition of both integers. With that out of the way, we'll close our simulation, clear our current macro, and create a new function block. If you remember part 1 of our macro series, we discussed where to define a function block within our macro workspace. If you haven't seen part 1, we'll review that now. The correct format of a macro built within our macro workspace is to list global variables first. These will be placed above our macro command main and above our function blocks. Global variables can be used within any of our function blocks or within the main function of our macro. Below our global variables, we'll create a new function block. To begin, we'll type sub. This is followed by our return variable's data type. I'll define this as a float. And then we'll define our function's name and our parameters. For this function, I'll make it slightly more complex than our first function block. I'll name this one C2F, and its purpose will be to convert Celsius to Fahrenheit. I'll define our parameters as float data with variable C, after which I'll hit enter and move to the next line, where we'll define our local variable F, which will also be float data. With both variables defined, we'll create our statement. Our statement will be F equals C multiplied by 1.8 in parentheses. And then we'll add 32. After this, we'll add a return command and return our F variable when we call our function. And of course, we'll add our end sub to close our function block. Now within our macro command main, we'll add a float variable and name it result. And below this, we'll assign our result variable to our C2F function. Within our function's parameters, I'll enter 10 so that we can test our function. And to finish our statement, I'll create a set data and set our result variable within our LW0 address, after which I'll save and compile our macro and then exit our macro workspace. Before I run our simulation, I'll need to change the data format of our numeric object to match our float data type. And with that configured, I'll run our simulation from within our macro. Since we haven't defined a variable, and we're using a static integer value, executing our macro will return a static value of 50, which is an accurate conversion from Celsius to Fahrenheit. And with that confirmed, I'm going to close our simulation and reopen our macro. I'll copy our function block so we can bring it to our function library. I'll explain why in a minute. With our function library open, I'm going to select New and then copy our function into our function editor. Afterwards, I'll save and compile my function block and exit our macro manager. On our project window, I currently have one numeric object. I'm going to copy this object and add an identical one right next to it. I'll select our new object and click our Format tab. In the center of this object, we can access our numeric scaling, one of which is done via macro subroutine. After selecting our subroutine, we're given two different ways we can run conversions. For this example, I'm going to select a read conversion, and in our drop-down menu, I'll select our C2F function. Once this is configured, we'll go ahead and apply our changes and then run a simulation. You'll notice our simulation boots with one object at 0 and the other at 32. Our object at 0 represents Celsius, while our object at 32 represents Fahrenheit. And upon entering a new number into our object at 0, we'll see the Fahrenheit change accordingly. Since we've covered so much information related to function blocks, let's recap some of the important topics. Macro function blocks, also referred to as subroutines, can be built within the macro workspace or within our function library. Saving function blocks within our global library will allow these functions to be used later and ensures that they're accessible within other projects. Function blocks are mainly used to reduce lines of repetitive code, but can also be used to perform read and write conversions within a numeric object. Now that we've finished our introduction to function blocks, I'd like to discuss macro debugging using our CMT diagnoser. To begin, I'm going to open our macro manager and then select the macro we created earlier. With our macro workspace open, I'm going to select Offline Simulation in the bottom right corner. By right-clicking on our simulation, I can open up our CMT diagnoser, and with that open, I'm going to switch to our Debugging tab and begin our demonstration. As I mentioned earlier, our Macro tab will allow us to execute and debug our macro. We'll begin by selecting our Debug section and adding some breakpoints within our macro. Breakpoints will define each line that our debugging tool will stop at before continuing on through your function. Now that I've finished, I'll select Start Debugging and then switch to our Execute tab and execute our macro. Once executed, we'll notice a red dot appear at the top next to our Debug tab. And now we can start debugging our macro. In our Debugging tab, I can access and debug any macro within my project by selecting from our drop-down list. And by selecting the Start Debugging button, our debugging tool will transition line by line until a breakpoint is reached. Our Stop Debugging button will allow us to end our debugging session, and our Break button will allow us to pause macro debugging manually without reaching a breakpoint. Next to this, we have a Step Into and Step Over button, which will allow us to debug each line of our macro individually. While the Step Into button is in use, our debugging tool will enter and debug our function block and return its result. Whereas the Step Over button will debug our macro line by line, and upon reaching a function block, will return the result of our function without entering and debugging the block itself. While debugging, we can add watch variables within our watch dialog box. As an example, I'll go ahead and add our result variable. This is where we can monitor the output and return value of our variables to ensure they function as intended. And our output menu shows system information and trace output, which we'll discuss in one of our next videos. For now, I'm going to make an online change to our numeric test value. Once finished, I'll close my diagnoser and then close my simulation. As you can see, the system prompts me to save our macro's change and then returns us to our macro workspace. Upon returning to our macro, our test value has been updated and our change is visible in our macro workspace. I'd like to note that online changes to your macro can only be made when running a simulation from within your macro workspace. Although you can run a simulation and perform macro debugging from your project tab or from within your utility manager, online changes will not be possible. While we have our macro workspace open, I'd like to demonstrate a few examples of data conversion. Let's clear out our old macro and create some new variables. I'll start by declaring another short, and next I'll declare a float, and then I'll create a character array with 4 elements. Now for most data formats, conversion can be done with one of our API functions. As an example, I'll open our API manager and select our data conversion category. After which, I'll open our drop-down function list to reveal our conversion functions. We'll begin by selecting our ASCII to decimal conversion. And looking at our example, we can see that the general format of our function's parameters is to list our character data first, and then our numeric data, followed by the array size of our character variable. For our numeric variable, I've chosen our short variable, but I could have used this function with our float variable too. Now I'll need to go above our new function and create a getData function for our character array. I'll start our array at LW0, and below our conversion function, I'm going to set our short data into our LW2 address. With that configured, we'll save and compile our macro and create our ASCII and numeric object. In creating our ASCII object, I'm going to specify our data count as 2 words because the size of our array is 4 characters. Since our numeric object is listed as a short integer, I'm going to make sure my data format is specified to 16-bit. And with everything properly configured, I'll go ahead and run our offline simulation. With our simulation open, I'll enter an integer value into our ASCII object. And as you'll notice, the value is converted to numeric data and transfers over to our numeric object. I'll go ahead and close our simulation and reopen our macro. And we'll create another example where, in this case, we'll go ahead and convert our decimal to ASCII data. To do this quickly, I'm going to move our get and set data functions and change them both to their inverse. I'll remove our old conversion function and replace it with a new function from our API function manager. For this example, I'll select our decimal to ASCII function. Ensure I select the correct variables in the appropriate order, and make sure my data count is set to 4. With this properly configured, I'll select Save and Compile and run an offline simulation. Since I've switched my get and set functions, I'll enter my data into our numeric object this time. And just like our last example, our data conversion is successful and our numeric data is transferred into our ASCII object. And while many conversions require the use of functions from within our API manager, there are certain conversions that can be done without complication. As an example, we'll close our simulation, and within our macro workspace, I'm going to remove our function and instead make an assignment stating that our float variable is equal to our short variable. Next, I'll change our set data's variable to float and our data count to 1. And as it's displayed, this macro will convert our short data to float data. I'll save and compile our macro and navigate to our workspace so that we can change our ASCII object to numeric. And with that configured, we'll run our last simulation. As before, you'll notice our conversion works as intended. And with that said, data conversions within the macro workspace are all fairly similar, and understanding the general format of our API functions and non-API conversions can really help you get familiar with our macro syntax. If you found this tutorial helpful and would like to see more, head on over to our YouTube channel and select the playlist tab. Feel free to check out our website as well for free demo projects, user manuals, and more. Thank you for watching.